technique to differentiate these is called logarithmic differentiation. This does not mean differentiation. This does not mean that you're just taking the derivative of a logarithm. Okay, this is a technique unto itself. A derivative of a logarithm is called derivative of a logarithm, or differentiating a logarithm. This is called logarithmic differentiation. Okay, it's its own technique. So we'll use an example from the textbook. What do they got here? 43 through 50. We'll take 43. X to the 10x. X to the 10x. So the basis of the variable is x. The exponent is 10x, another variable function. Function raised to a function. Meaning non-constant function raised to non-constant. Okay, I'm falling down. All right, so the first thing you do is take a logarithm of the function. Okay. So forget the ddx for 1 second. This is what we're supposed to accomplish. And before we do that, we're going to take the natural log of the function itself. So first move, natural log of x to the 10x. Right? Natural log of x to the 10x. What does this do for us? Well, it makes it even more complicated. Now it's got a natural log attached to it. Right? What you've done here is you have put x to the 10x inside the natural log. So this thing, the input has an exponent inside a natural log. What can you do with an exponent? Take 10x outside, right? All right. So this is the same as 10x ln x, according to the third log property I wrote on the board a minute ago. Okay. That an exponent on the inside is a coefficient outside. It works even for functions, not just for numbers. Now we have this expression. I want to differentiate this. Okay. So I want to take d, oh, not y, sorry, d dx of our altered function, 10x ln x. Again, first thing you do is take the logarithm of the function itself, alter it so it no longer has the tower portion of it, right? It's no longer a tower. It's just a product, right? 10x times ln x. And then take the derivative. Remember, you have altered the function though. You're not, this is not the same as this, right? This is inside a logarithm, and it's outside a logarithm. So you're now differentiating not your original function, okay? Differentiating a changed function. So we have to fix it in a second. So this is fairly straightforward now, it's just a product. So you should get, what? First, times the derivative of the second, plus the second, and x, times the derivative of the first, times 2. Okay. All right, so x over x is 1, so we end up with 10 plus 10 ln x. We don't have a factor of 10, so I'll take that out. So it's 10, 1 plus ln x. All right, agreed? We have now found the derivative of the natural log of our function. Okay? You guys with me on that? So now it would flow like this. When you take the natural log of the function, you're going to write it as ln y equals ln x to the 10x. So the y equals x to the 10x, that's the function you're starting with. And you're taking the natural log of both sides in a sense. Okay? Natural log of both sides. It ends up looking like this. So now you can take the derivative of both sides. So you need to take the derivative of ln y. That's going to equal the derivative of your changed expression. Now, the derivative of ln y, the reason this technique comes after chain rule and implicit differentiation is because you have to do implicit differentiation right now on the left-hand side. The right-hand side was no big deal. It was all x's, so it's the regular case. But over here, the derivative of ln y, right? Y is an implicit function of x. You actually know its representation here. Is going to be the derivative over the original. Y prime on Y. Y prime on Y. Every single logarithmic differentiation problem, the left-hand side is Y prime over Y. Okay? So it turns out that Y prime over Y, the left-hand side, is going to equal, big equal sign there, the 10 1 plus ln x. So now, what am I going for though? I want the Y prime. So I need to multiply both sides by Y, so I have Y prime by itself. It's one of the simplest implicit differentiation problems you could possibly do. And that's really all it is. It's a very simple implicit differentiation. So now you have Y prime equals the original function Y, because you're multiplying it over here, times the 10 1 plus ln x. But in these cases, you know what Y is. You know it's x 10x, so you should put that in for Y, since you know its representation. So Y prime is going to be this 10 times Y, which is x 10x times 1 plus ln x. Okay? There's our derivative. Let's do another one.
Wait.
Yep.
Y equals 10x to the 10x?
Y equals 10 times x to the 10x.
Oh.
No, I'm sorry, no. You're saying Y prime or Y? You say Y or Y prime?
Okay, I just didn't. Okay, never mind.
The original Y is this, so I'm substituting that back in here, right? For that Y. Since I know what it is in terms of x, I should use that. 69, x to the cos x. This should be very similar. So I want to find ddx of x to the cos x. Again, since both the exponent and base are variable, it's time to use logarithmic differentiation. So I'll make it clear this time. We'll start with y equals x to the cos x. You're going to apply natural log to both sides. ln y equals ln x to the cos x. That allows you to pull down the cos x to the front of that expression. So ln y equals cos x times ln x. Okay?
Use a product rule.
Now it's product rule time. The product rule on the right-hand side. On the left-hand side, when you take the derivative, it's always going to be y prime on y. Okay? Y prime on y. So now we're going to take the derivative of both sides. So d dx, just like we did with them implicitly yesterday. D dx, both sides. So this side is y prime on y. The right-hand side is a standard product rule. So first times the derivative of the second plus the second times the derivative of the first.
Yeah.
Can you slow down a bit?
I don't know.
I don't know.
That's a good question. Oh, look at this kid with a scooter right now. Give you a chance to catch up. One of those three-wheel scooters, make sure it didn't fall down. Got a little Johnny. Almost the car. Almost the car. Come on, buddy, you can do it. Oh, it's me. Look at him go. Oh. Wife's taking pictures of him. You got some trees too. They look thirsty down there. All right, ready? Time now?
Yeah.
All right. Cornell, you caught up?
Yeah, I'm not. I mean, I wrote it, but like.
Looks like you're pigging out instead of trying to follow along.